Perfect. So, welcome everyone. And today, what we are going to do is we are going to just explore this board right here, which is the PICO 2 or PICO 2. And you know, it's been like few days that I ran into this board, and at least this has excited me the most in recent times. And the reason to that is this chip right here, which is the RP 2350. So if you like you run a Google search by this name, you will get like the spec and all of that corresponding to this chip. And what's special about it is that it has got total four CPUs, so four cores, and two of them are ARM M33, and the other two are the Hazard 3 RISC 5 RV, well, RV32 cores. And so the interesting thing is that there can be two cores active at any given time, either two M33 or the two RISC 5 CPUs or one of each. And then what is even more interesting is that ARM Cortex M33 happens to have something called trust zone, and trust zone is a very popular security hardware security feature that the V8 line of ARM architectures offer. So this is also seen in the ARch 64 or A class application grade CPUs. And application grade CPUs are essentially the ones on your phone, tablet, Macs, then the Copilot PC. They all implement the ARM A 64-bit architecture, which also has trust zone. Okay, that said, so this is one interesting part. The second one is that M33 is, well, kind of the latest uh, architecture. Well, it is based on the latest architecture, which is V8 for the M class CPUs. I believe there is V9, which is out, but V8 is, in my opinion, the latest in terms of getting the CPUs in the market. Then, okay, fun part. Why do we care? Well, first off, trust zone. We'll be able to do some security related interesting things in the future, of course, not as part of this call. The second one is that it has got RISC 5. So we can learn two architectures on one single board, and also we can learn multi-core programming. So all on one board. And then apart from all of this, the multi-core boot is something that is very interesting. So one single board, so to speak, to handle many different learning experiences. All right, so any questions at this point? Well, you can maybe raise your hand, and I see that there are too many people on the call today, so not sure if I can unmute all of you. Oh, actually I can unmute all. Yes. All right, so anyone who wants to speak up can talk. Okay, no questions. Perfect. So what we are going to do as part of today's call is take a look at the documentation, and I'm going to also explain what's on the screen here. So this is essentially the board. It's $5, I suppose, roughly, and in India that's like less than 1,000 rupees. So you can get that board for like really cheap, in my opinion at least. And what you see here, let me just change the color. Okay, let's get a nice bright color. Okay, so what you see here is called the debug probe. This is also developed by the folks at Raspberry Pi. And what you see here are two ports. One of them is for hardware debugging, and we'll talk about that in a minute. So this is for hardware debugging. And the other port, which is right here, and connected, and then it goes behind the board and connects right here to the UART. And UART is, for those of you who don't know, universal asynchronous receive and transmit. This is where we'll get to see logs, if any. Usually we print logs on the UART, and during the boot up and the bring up phase, it helps. And this part here, it's connected to an Ubuntu machine right now. And that Ubuntu machine, okay, let me see if I have it here. Yes, that Ubuntu machine is right here. And we're going to run some experiments in a bit. Um, but okay, so yeah, this is the debug probe. It'll help us control the execution of the CPU, kind of, single step the CPU through our program, understand what's going on. Things of those nature become really, really simple if we have a hardware debugger. This is also what we'll use with GDB. And then I'll just briefly talk about the setup. So we have got the Ubuntu machine that has got a USB connected to it. That's connected to the debug probe, which in turn has two ports, and one of them is on the UART. The other one is on something called single wire debug, and both of them are connected to connected to the PICO 2. Right. This is the setup. So now the thing is, within this Ubuntu environment, we have two terminals, or we will have two terminals. And on one of them, we will run OpenOCD. And OpenOCD is Open On Chip Debugger. That's what it stands for. It will kind of communicate with this debug probe and then indirectly communicate with the debug port on the PICO 2, and also whatever is coming from the UART will be routed, um, so to speak, to our Ubuntu machine on the same wires. Okay, so OpenOCD essentially can connect to the debugger on the chip, which is a hardware debugger. It's a hardware unit, and we'll take a look at that in a bit. But the idea is that OpenOCD will control the debug circuit. And what OpenOCD does is exposes a socket, or exposes a port, so to speak. And to that port, we can connect GDB. Right? And this is also like the typical flow that we have been following in all our courses, except instead of OpenOCD, we tend to have QEMU, which is an emulator which runs locally. Okay, so long story short, we run GDB, and then that connects to OpenOCD. GDB commands OpenOCD, and OpenOCD connects or talks to the hardware circuitry on the PICO 2, and then controls the execution, hardware execution of the CPU. All right. Any questions at this point? Well, today's session is going to be like a rapid fire, uh, me and other two blabbering kind of thing. But if you have questions, feel free to jump in. All I wanted to do was introduce this board and encourage you all to take a look at the documentation, because I think there is a lot that this can teach us about the generics of firmware engineering. All right, any questions so far? All right,
Actually,
ma'am.
I think I had a tidbit to share. So
Oh,
the
go ahead.
debugger itself is also another PICO board.
Oh, yeah.
So
Yes.
I mean, that's how cheap it is. So instead of designing a different debugger, the Pi folks thought, the Raspberry Pi Foundation folks thought, hey, why not throw in another PICO itself?
Right, and in fact, I'll show that. So if you can see, there is a Raspberry Pi chip
Yeah,
right here, right? And so yeah, the M class CPUs are so cheap. They are like dirt cheap, that it makes sense to uh, use that M class CPU with the firmware on it rather than designing a hardware. It is that cheap.
yeah, that
And
makes sense.
more importantly, this I think has the RP 2040.
Yeah,
And
yeah.
RP
Mm,
2040 is,
mm.
Mohammed, you can keep me corrected here. which is,
Hmm.
I think this is M0 plus based.
That is right. I think
Uh,
so. Yeah. I think it is a dual core, but those are M0.
M0
Don't have
plus,
the
yes.
trust zone enabled.
Yeah. By the way, M0 plus is a very tiny CPU, very tiny M class CPU. It consumes like very little power, and I don't have realistic, practical numbers with me right now. What I read was it is such a low power CPU that it makes sense that you use this CPU and firmware to mimic hardware, right?
Hmm.
What do I mean by hardware? Well, instead of writing your state machine as an RTL or using gates and a huge circuit using gates digital electronics, instead of doing all of that, you can just have the CPU with the firmware running on it, which mimics the state machine of this hardware, and that would be cheap and power efficient both. So cool. Any more questions or comments?
Piyush, one question.
Yeah.
Can you?
Yes.
So I'm using a Mac operating system right now. So how is the compatibility of this whole setup with the Mac?
Oh, cool. So, I was using, I was trying to program this on a Mac, on my Mac directly. That didn't fly uh, as well as I would want it. And I was in such hurry that I have this, hypervisor running here, which is, Parallels, that's the software, and that is running Ubuntu. And okay, let me just quickly show you how I do things. So it's running, oh, it is, just a moment. Yeah. So it is running Ubuntu. Whoa, what is happening? Just give me a moment. So yeah, let's see. Yeah. So the hypervisor is running Ubuntu in it. And what I have done is connected or routed the debug probe into this virtual machine, right? So if I were to do, let's see, right, if I were to do LSUSB, I do get the debug probe here. And what I tend to do then is just work with this. So that's how I operate. Does this answer your question, by the way?
Yep, thank you.
Yeah, slightly twisted story. Um, what I was trying to do yesterday was to get this to work on Mac, and then the problem was that I had to compile OpenOCD locally. That didn't go well. I got tired and frustrated. I just moved to this setup, and that works really well for me. Okay, any more questions or comments at this point? All right, perfect. So moving on, we are going to do OpenOCD related something. We have about 45 minutes, but then what I wanted to guide through was this documentation, and this documentation is worth skimming, if not anything. And this is the data sheet for the RP 2350. And what I want to do, and Mohammed and Nikhil, you can also jump in. What I want to do was show you some parts of this document which are very relevant, not only for this board, but it's kind of like a general philosophy in terms of implementing hardware. Okay, so, and it's also like a good exercise in terms of given a new chip, how do you work with it? So the documentation is really, really great. And we'll start off with the introduction part and few things that I want to highlight. So, dual core M33 and Hazard 3 processor gets clocked at 150 megahertz and well, has some SRAM and things like that on board. Um, what is useful for us is, well, UART definitely, because this is where we would want to receive logs, if any. Then there's PWM channels, a lot of those. Then there's something called PIO, programmable input output. So what these um, PICO folks have done is they have provided us with an ability to program a GPIO with a function. So what do I mean by function? In general, what happens is you will write a state machine in hardware, or sorry, in software or as a firmware. And so the software executes and controls the IO. Maybe you want to, let's say, toggle a pin n number of times. So if you want to do it in software, you have to kind of, toggle it, then wait for some time, toggle it again, and so on and so forth. So what these guys have done is given us a programmable hardware, something like, imagine DMA, the way DMA can be programmed. Um, so they have given us a piece of hardware that you can write the instructions for, and it executes those instructions in a loop. And so what happens is you can essentially deploy that GPIO toggling function to a hardware piece, and your software can, continue to run without bothering about it. So we'll see interesting use cases of that much later when we talk about, designing using this chip.
So
Oh,
Piyush, can we say it's like a coprocessor or a very basic
yes,
coprocessor of sorts?
yes, yes. So you can definitely imagine it to be a coprocessor. So you've got M33, M33, and as we'll see somewhere there is PIO. So one of these guys can go program this PIO, and then it can just control a GPIO, much like, as Mohammed mentioned, a coprocessor. A coprocessor is essentially a friendly processor that you can deploy a workload on. Uh, an example can be the floating point unit. Okay, this is something that you should spend, time on. So this is like a map of the entire chip, a logical diagram. So all the peripherals are here. Uh, what is very important is that there is something called bus fabric. Okay, fabric, and this is also called the interconnect. Things that we have been taking a look at in our previous tech sinks when we talked about the memory models and things like that. I was referring to the interconnect or the bus system. Well, that is this. And these wires that you see here, these lines, well, these are not, let's say, simple wires. They are buses, and these buses happen to have a protocol of their own, and they are called the AMBA. They are based on the AMBA specification. Then you have something called APB, AMBA peripheral bus. There is something called AHB, AMBA high speed bus, or high performance bus, and things of those natures. All right, any questions or comments so far?
Hi, Piyush. Can you
Hey,
hear me?
yes,
Hi. Okay. So I just have this question. So if we have four cores on this, I'm pretty sure we can configure two at the moment because both of
yes,
them are ARM. So can we run
yes,
parallel processes with these two cores using both of them
yes,
together at the moment?
yes, yes, that can be done. I right now do not have enough details to tell you how you can launch both the cores and have them run, let's say, different programs, but that is certainly possible. That is, in fact, the whole point of having two cores. Usually, what happens is one of the cores will end up doing a lot of DSP operations, while the other one runs like an operating system, and that's how the cores are usually used. Um, but yeah, answering your question,
Like
yes, two cores can run two programs
maybe
parallelly.
my hunch would be like if we program the reset vectors of both the cores differently,
Yes,
that would
yes,
be my initial hunch.
that is correct.
Hmm.
If we are talking about the M class CPUs, then for both of them, if the reset vectors are different, then they go off in their own direction, doing very different things. And but the answer to the original question is yes. Two cores can execute two programs simultaneously. That is possible. All right. Any more questions or comments? And by the way, the processor subsystem is right here. There is processor 0, processor 1. Now, from my readings so far, you can pick between an M class, the M33 or RISC-V RV32, that is, on processor 0, and you can pick one from proc 1. Okay, so I'll just erase all of this real quick. By the way, those of you who are new on the TechSync call, this call is kind of, it has like a hard deadline of 1 hour. So around 11 o'clock, if we do not conclude, the call gets auto disconnected. Um, so yeah, that's just like the background. Okay, so what other things do I want everyone to keep in mind? Okay, so there is the memory here. What is interesting is we have got the OTP, which is one-time programmable memory. So this usually has some configs, things like your keys, things like certain boot paths. Uh, there's something called vector table offset register, so the initial value of that can come from the OTP in general. Then there is a ROM where the Raspberry Pi people have their own code, and as part of that code, so what happens is the CPU boots up one of the CPUs, which is hidden from us right now, or at least it might be in the documents. I haven't hit that point, so I do not know the details. But what happens is one of the CPU starts off mostly an M-class CPU. It tries to boot further, then it tries to essentially load a user image. And if these keywords sound alien right now, rest assured, eventually with time, everything will make sense. But the idea is that the M-class CPU, one of the M-class CPU starts booting up using the boot from the ROM code here. And then what happens is it'll check what is the image on the, I suppose it's on the SRAM, it checks it that way. So what is the image programmed on the SRAMs? And then from there, what it does is if it is a RISC-V image, it will reboot with the changed configuration that a RISC-V image should, RISC-V CPU should boot up. So the ROM code is used uh, in some sense for all of that. They also talked about Flash, and I believe this is also implemented using Flash. We'll see. Then there is something called XIP or slash caches. So caches are temporary locations. So, and this is like a fast memory. So reaching out to the SRAM is slow. So what happens is the CPU will keep stuff in the caches. There is a concept, something called temporal and spatial locality. So when you look up or try to understand what caches are, these are two fundamental phenomena that it tries to leverage. But anyway, the XIP is interesting, which is execute in place. So usually caches is, well, how do I say? Let's return back to this later. Mohammed, do you want to speak to XIP in case you happen to?
Yeah, I think I have some bit of info. So XIP, if you see, XIP and caches are connected to the QSPI block at the end, which is interestingly connected to an external flash, which is outside the chip.
Right.
So what it does is it opens up, a very small window for which is sort of memory mapped to the external flash.
Mhm.
And that is
Right.
what XIP stands for, like execute in place. And that window can be mapped, as we go forward in the code. But then as far as the Raspberry Pi, the cores are concerned, it's like it's just getting a view of some window into the flash.
Right. And when we talk about the window, it simply means that there is an address range from, let's say, A1 to A2, which you can map to various regions of your
Right, right.
external flash.
Yeah,
All right.
and so
So,
let me add some more bit. So there are two types of cases. Sometimes you'll load the external program into an internal SRAM and then execute from it. Because it is SRAM, you can do read, write, and whatever other things. You can also
right.
uh, do offset changes or relocation. But in the case of execute in place, you are basically getting the data and executing right away, and that's why it's called execute in place. But there is no SRAM involved at all. You get the instruction and execute right away. So you cannot do any relocation or any dynamic allocation. So when you are
Right.
loading the value, you know all the offsets and everything.
I see. Okay. Yeah, that's an interesting one. Right. Cool. So then moving on, there is this SWD, which is single wire debug. And interestingly, this will go into, I was hoping that they would have like a debug uh, block diagram here. It's on some other page, but this goes into the debug circuit. And then the debug circuit essentially controls many different, well, it controls the CPUs and also, the interrupt controller and few other parts. That's that, I think. What else? Mohammed, Nikhil, do you want to add anything else which is important? Oh, by the way, just a quick one. So here's the PIO, and they have three PIOs. So essentially, three hardware circuits that can be converted into co-processors of some sort.
As part of boot up, you might want to just focus on the UART.
Okay, where is the UART? Right here. Yes. So what about the UART?
Like as part of the boot up, we'll be touching that part, and
Oh,
that's how you'll.
okay. Yes, yes. So as part of the boot up, usually the prints come out on the UART. So that is one interesting bit of hardware. Um, then there is something related to power supply, which we'll come to later. And interestingly, this one also has a USB. And on the USB, the PICO will emulate like a storage. So when you connect it to your Windows, Mac, or Ubuntu, it will show up as a drive. And in that drive, you can drag and drop your programs. And what it does is it then flashes that program internally and in kind of, reboots the system. So they have made it very easy to program this chip. You can simply drag and drop the compiled binary onto a drive. But we obviously will do things differently. We will try and flash using OpenOCD. Okay, so what else? Let's look at the bus fabric. Yeah, this is something important. Well, if not important, at least the diagram gives you a sense of how, in general, the embedded systems or the programmable system looks like. So we have got the core 0, core 1. This is the instruction path. This is the data path. What is worth noting here is the direction here is only inwards, which means instruction only come into the CPU and then it executes it, but data is bidirectional, so reads and writes. What happens is it goes on to this AHB phi crossbar. Crossbar, you can think of it like a railway track uh, configuration thingy where one track can be connected to another one to route a train onto a different track, let's say. So a transaction coming from here can be routed n different places, and then you can imagine that there's like a switch matrix which connects different bus systems or different entry and exit bus with each other. So that's like the idea behind crossbar, but it is based on the AHB phi protocol. So if you're looking to get a sense of what AHB is, go after AHB 5. Right? AMBA, high performance or high speed bus. Okay, then just a moment. Yeah, what else? Well, the diagram itself is very interesting. It tells you who is connected to what. And as you can see here, the APB is the AMBA peripheral bus. And so a transaction coming from here, for example, gets converted from one protocol to another. And when I say protocol, you can imagine this to be, packets, address and data going from the CPU down towards the peripheral. But here, there is a hardware block that translates the protocol. And because APB is slower, things work out. And so here what is happening is at a time, this is like a demux. So given one input, the packet that's coming, it will get routed to one of these, depending on, again, the address map. Okay, any questions or comments so far? Oh, I see there is something in the chat.
We are
Okay.
answering offline whenever we can.
Oh, okay, perfect. Thank you for doing that. And what else? So let's see.
I would like to maybe add one more thing. So you can think about AHB as like a 4-lane highway with a lot of bandwidth possible and any high-speed operations. with respect to the CPU, DMA, and SRAM will be happening there. But think about APBs as like a small roads where the bandwidth is not required so less. So because of that, you will have like maybe one connection from the high speed bus to the low speed bus, and all the small peripherals are kind of connected to the low speed. And that's why you see like a good mix of high speed buses, low speed buses, as and when the use case is required.
Right. Oh, that's a good one because if we see here, the USB, for example, is on the high-speed bus, and then the low-speed peripherals, SPI to C, are on the APB. That's a good one. Thank you, Nikhil. So what else? Moving on. By the way, this section is full of insights about the bus system as to how it operates and what all features it can have. So things like, atomic reads, for example, there is sections on that. Then let's come down to the address map, which is a common theme across all the tech syncs, that there will usually be an address map, and it essentially dictates what address corresponds to what subsystem or what memory section or what peripheral, right? And the idea of address map is based on this concept of memory mapped I/O. You have input and output systems that are mapped as if they are memory address, and reading and writing to those memory address might have a real world effect. And I'm saying might because depends on which address you read and write to. So if you're writing to addresses that start from what is it, 20 million? Uh, is it 20 million? Yes. So 20 followed by 6 zeros. Yeah, looks like 20 million. So 2 followed by zeros. So if you're reading and writing there, then, well, that's the memory region. But let's say if you are reading and writing to addresses which are around like after 5 all zeros, then we might be writing to I2C, UART, or PIO, and so that might result in a real world effect of the bits flying over a wire or something of that nature, or GPIO, toggling or things of that nature. All right, so the address map section talks about, where is what and what is the address of different things. For example, OTP, if you want to fiddle with that, read OTPs, for example, then this is the address to go after. And not only that, it's just listing the base address here. And down below in this document, they also talk about then, the details of what all registers you have, registers or addresses that can help you with configuration of the IOs or with respect to OTP, things of those nature, power, things like that. All right, any questions or comments?
Piyush, I have a question. You told about this XIP or cache block. So the cache is there for a purpose to faster access. So if you are fetching from the external memory some instruction and executing it right away, doesn't this slow the processor down or something like this?
Right. So the question to ask is how many instructions are we fetching? And usually what will happen is it'll fetch bulk of the instructions, keep them in XIP, and then execute from there one at a time. Nikhil, you
Okay.
can keep me corrected. Yeah.
Okay. Thank you.
Yeah. And so, that exact thing, you can think of it as temporal and spatial locality, meaning if I'm executing an instruction from location X, most likely I'll also execute instruction from X plus 4, X plus 8, assuming each instruction is 4 bytes. So X plus 4, 8, 12, 16. So it's like in the neighborhood of my target address. So that's spatial locality. And temporal locality essentially means, okay, there is a high chance that I execute the next instruction and there is no if condition. So that's like in time, I might execute the next instruction immediately. All right, any more questions or comments? We have about 25 minutes left. All right, moving on. Well, again, all of this is just to encourage you to go ahead and take a look at this document. They also point out the ARM-M architecture reference manual, so do take a look at that as well. We are yet to go to the Hazard 3, but let's move on. Let's see, what else did I want to talk on? Mohammed, do you have any topics that you wanted to touch upon?
I think I'm seeing a lot of questions on chat on the confirmation of what is the mode of setting up or booting up the cores. Either both of them have to be M33, both of them have to be RISC-V. So what I know is one can be, it's like paired into two, one hazard core and one M33, and there are like two pairs of or two bunch of these, and you can program one bunch either in M33 or RISC-V, or the other one could be independently toggled into other one. Piyush, if you can confirm this,
that's correct. Like I have also read something similar, which is you get to choose only two CPUs to operate at one time.
right.
Both can be ARM, both can be RISC-V, or it can be a crossover, which is
Right.
ARM and RISC-V, but
So
only
I think
two cores.
Two cores, yeah. So there were a couple of questions. One was why not all four of them at the same time to maximize the juice? I think the answer to that would be the reason why they're bunched together in pairs of two is they share a lot of common logic in terms of interrupt routing or bus matrices and all. So not all two of them in the same group can be turned on. So you have to choose one core from each of this, proc you saw on the figure in proc 0 and proc 1. So that was
Right.
one. I think there was another question.
Right.
Which I
So
think we have already
what
confirmed.
you mean is, well, actually, let me just. From what I understand, my imagination is like something like
Right.
so.
Yeah. That would be mine as well.
Right. So you only get to pick one CPU in either of the proc. Okay, what was the next question?
I think we confirmed sort of. Like, why can't we run all four at the same time? Yeah, all right, we are good to go.
Okay, perfect. So moving on then, well, there is section on debug. Oh, wait, from this diagram here, there is this, which is single wire debug port. And well, there is, I don't know about self-hosted debug APB, what that means, but there, just as a hint for all of us, there is something called embedded macro cell, and it's part of something called CoreSite. So look this up, and this essentially provides the information about the debug infrastructure. Oh, well, you have CoreSite right here. So it provides information about the debug infrastructure, the formal debug infrastructure that ARM provides. They also have specification on that. So if someone's interested to learn more about how systems offer debugability at the hardware level, that's one of the specs to go after. Again, they have some mention of self-hosted debug here. Didn't read through it. Programmer's model, my favorite. On this note, when we talk about programmer's model, one of the documents, again, based on the previous tech talks, one of the documents you should go after is this ARM Cortex M33 devices generic user guide. And this one document will guide you on everything that relates to M33 processor. And what you will notice is that this is so similar to the M3 that we have been studying. And the purpose of calling this out is that once you know one M-class CPU, you pretty much know all of them. There would be just slight delta changes that you can instantly catch. So here, for example, if we look at, well, I'm just looking for one diagram. Let's see if I can download the PDF real quick. Is this the one? I don't know. How do I download the, oh God. Okay, watch me struggle.
Yeah, on the left side, there's this download you can
This,
use. Yeah.
this one? Oh yeah, nice. Yay. So that's that. Okay, very nice. A colorful document. What I want to focus on here is just very quickly show you the programmer's model. Well, this should sound very familiar. Thread mode, handler mode, privilege levels. All of this, again, for those of you who are new, check back the previous textings. The recordings are available, and we talked about all of this. Right, this should again look very familiar, 16 to 20 registers. The only difference, well, not the only, there are many differences, but one of the differences is that we have stack pointer limit registers in the V8 architecture, which is M23, M33, M55. So we have those. Then, because there is security involved, there are shadow registers in the secure and non-secure mode. So initially we talked about the CPU being in thread mode or handler mode. Now the thread and handler mode exist, but two copies of it. One is non-secure, one is secure. And to separate both the worlds, to separate the code running in both the worlds, they also gave us few registers which have a separate copy in either worlds, secure and non-secure. And this entire concept of secure and non-secure relates to trust zone. And just a very rapid fire 101 about trust zone is this. You have a CPU, you have memory and resources. So what happens is we have got this AMBA bus, the APB AHB. So I'll call it AMBA. So what happens is you have one extra wire that is carrying one extra status, and if that status is 0, it means that this entire address that's generated is to be treated like it is a secure address. What does that mean? It means there is some part of the memory that is marked, and we'll discuss about what marked means much later, but it is marked to be secure. So if this bit was 1, then the transaction or the address is non-secure, and if that non-secure address happens to be of this region, that transaction is blocked. That's the idea of trust zone, that a secure data cannot be touched by non-secure code. Again, when we talk about details of the M33, we'll talk about how there is a secure world, how there is a non-secure world, how to jump between the both, what kind of code resides on the secure side. And a hint to that would be your thumbprint authentication, for example, usually should be done by the trust zone side. And the reason to that is you don't want the non-secure code to come read your thumbprint and then send it over the internet. IoT devices, for example, right? You don't want that. Okay, so that's that. Any more questions or comments? Again, we are 15 minutes away from end of call. So, okay. But again, M33 generic devices user guide, that gives you all the details, about 300 page long. You don't have to read every single line. But once you know one M plus CPU, understanding and ramping up with another M plus CPU, piece of cake. Okay, that's that. And then when you look for the Hazard 3, which is the RISC-V CPU, turns out it's an open source CPU. So you got the entire implementation of that CPU available. And so if someone's interested into how CPUs are written, well, this is the directory to go after, right? You've got the CPU port 1, port 2, the CSRs, the configuration and status registers. Well, they are implemented like so. This is how people write digital hardware. All right, what else did I want to talk about? Let's see. By the way, any questions or comments at any point, just be sure to ask those. What other interesting thing did I want to call out here? Let's see. Okay, there is one beautiful picture somewhere about how to debug the board, a board or the CPU. Let me just try and find that. And once I find that, we'll go on to the demo and then conclude the session for today. But the challenge is finding that diagram. And okay, debug. How do I search here? Oh no. Let's see. In the meantime, if there are questions or comments, they are welcome. Is there a way I can do something smart? Anything. Okay, clear, recent, okay, fine. Cancel, outline, bookmarks, nope, did not have those. If anyone has this open on the side, then do let me know if you find the debug section. So the debug section in this, in fact, let me just go to Google search and then type debug probe and PICO 2. Let's see what comes up. Hopefully I get some information here that I was looking for, and then I can just quickly.
Are you looking for the diagram at page 35?
Oh, thank you. Let's see. First off, where are the page numbers? 1. Okay, that's the start. Page number 35, you said, right? Let me go 35.
Oh,
30. This one you're saying?
yeah, there is some description about how the host connection is going. Yeah, there's a diagram at the start.
Okay. No, not this.
Not sure if that's right.
There is a colorful one that essentially shows this.
Oh, okay.
And then next to that is like the command, that OpenOCD command that can be executed. So let's see. Let me try and find that out real quick. And if I cannot, then, well, sad. Uh, hmm. Let me search through the images. Yes, something of this nature. I think I found it. Perfect. So this is how it is. This is how it is to, oh, by the way, which board are we talking about? Doesn't matter. Let's see. Yeah, this is how exactly I have connected also. This was the diagram I was looking for. This again, this page guides through how to use OpenOCD. And so exactly this is what I want to use. By the way, some FYI here. So OpenOCD lets us connect to the board, obviously to debug, but also we can use this -C flag to issue a command. And using that command, we can also upload a binary. So initially I had mentioned that PICO 2 folks allow us to drag and drop our binaries, but that's not necessary. We can also do this. So what I'm going to do now is copy this and then hope and pray that it works. So, all right, let's see. And this is also where so what I want to show is essentially us using OpenOCD and how in the future this might help us. Okay, let's see. So I want to get rid of this. Hopefully it connects. Okay, perfect. So it doesn't have some very specific thing. I just hope the Murphy's law doesn't kick in now. And
Now you can go to CD's OpenOCD because the paths are related.
sorry, you were mentioning what?
You can just go into the SRC folder, CD SRC.
Yes,
Yeah, and
but
now
I
just tap it.
suppose, yeah, that's what I
Now don't do it
did. But let's see. Okay, you're saying
because
the
the CFG
interface
paths
is
are, yeah.
right. Oh, one other thing that I need to do, which is change this to 53. Sorry, 50, and this needs to be 23. Doesn't work. Why? Because something's wrong. Okay, what is wrong? So welcome to live debugging, and if it goes well, we'll be able to see this work. If
If you
not,
see a TCL folder inside that, you can just add minus minus search TCL if that is the case.
where?
Where do you see where is the file? Like, do you see an interface cmiss.cog file? It should be there somewhere.
The this you were saying?
Yes. Can you find
Okay.
that file? Where is that?
Yes. Oh yeah, I think you're right. There was a command that related to TCL. Let me do this real quick. Nope, not there.
Then maybe you just have to go back.
Yes. Okay. Yeah.
Okay.
All right.
So just add minus minus search TCL and don't do cd.
Where you're
Minus
saying where
minus
do?
search TCL.
Okay. Minus minus
Search
search
TCL.
TCL. Okay. And what else do I add? Do I need to retain the interface slash?
Yeah. That is related to TCL.
Oh, perfect. Thank you, Nikhil. Such a savior. Thank you for joining the call today. So, okay, what we see here, and actually I should also show. So you see that this thing has lit up. Let me control C this. Okay, so what I want to do now is do this, and what happened? Well, it should have lit up. It has. It hasn't, because did I screw it up? Okay, never mind. Okay, very nice. Right, so it has lit up now, which means the debugger is active. And what OpenOCD has done for us is it has started a GDB server, and we'll be able to debug the core 0. So I'll go to another terminal window and then write GDB multi arch, and then I would say my target is remote, and it is on localhost port 3333. And the moment I do that, it has connected uh, to the chip, the RP2360. What we see here are the two CPUs, and CPU 0, the one in bold, is the one that the GDB is controlling right now. And what I wanted to show you was that we see the exact map of registers as we had seen on the M3 CPU, except there are few others which are NS and S. So that is just secure and non-secure. All right, so that was about it in terms of what I wanted to show. There is I don't have a sense of which, well, obviously it is running the Blinky binary, but I'm yet to map the source code to the GDB so that we can see the C code and then do like a live debug. But all said and done, I just wanted you guys to take a look at the new RP2350 and just wanted to share my excitement. All right, any questions or comments? Okay, so there is a question. Is memory protection MPU config handled by software? Well, the answer to that is yes. Configuring the MPU is optional, but if it needs to be configured, well, it's the software that needs to configure it. Also, can we look into how to create MPU regions for FFI? What is FFI? But can we look into MPU configuration, uh, freedom from interference? Okay. Oh, okay. I think Nikhil knows a lot more about that. Nikhil, do you want to take that?
Yeah, so typically when you want to run multiple software entities together, you want to ensure there is FFI, that is freedom from interference. Like you want to guarantee that one set of software does not cause issues to the other set of software. And for that,
Fair.
sometimes the guarantees are done in software, sometimes the guarantees are done in hardware, and there are additional set of settings to do that.
I see. Okay, perfect. Well, so at least I haven't touched upon FFI, but interesting, and we can talk about that. Cool. So any more questions or comments?
Hi, Piyush. Just one more. Probably in this architecture, maybe there is no branch predictor or reorder buffer or something like that. I think it doesn't support those blocks, I think, isn't it?
Okay, interesting. So maybe the architecture doesn't dictate that. The microarchitecture is the one that may choose to do that or not do it. So what I mean is, I suppose the M V8 architecture doesn't stop you from how you want to implement a CPU. What we should be looking at is maybe the technical reference manual for M33. I think that will have more details on whether or not the branch prediction is available. And from what I can tell, most likely the M class CPUs are free to implement branch prediction, given that they have the barrier instructions for instruction. So instruction synchronization barrier. There is an instruction for that. And so I'm expecting that branch prediction should be a thing.
Okay. Yeah. Thank you.
Also, the fact that there is a XIP cache, I would expect there is some kind of a predictor to make sure that the cache is really utilized.
Makes sense, yeah.
I think in A class, it's most commonly implemented. I mean, it will be available. But in M class, it's really interesting to see this cache is present. And so that's why this question popped up in my head.
Interesting question, though. I'm definitely going to go take a look. Yeah.
Yeah, sure, sure.
Cool. Any more questions or comments? We are like about time, 2 minutes from the end of call. All right. So if no more questions or comments, I just want to invite you all on the Tech Sync on 20th, 28th, and Nikhil here, who is on the call today, he is going to present on PCIe. And so far, 28th May is the date. Just in case things change, we'll push that out by a bit. But yeah, do join in to kind of understand and know more about PCIe. Nikhil, do you want to say anything about that?
Yeah, I'm planning to have this first session as very much introductory, going into details of why PCI exists and what are some of the not so commonly known things about PCI. And of course, there's enough documentation to read about details of the protocol, but I wanted to talk about like why it exists, how do we program, and what it does. So join in for that.
Perfect. I think then with that, we can close the call for today if there are no more questions or comments. And all right, I think I'll just wait for a few more seconds. And if not, then yeah, thank you everyone for joining in. And hopefully this was, somewhat useful and exciting. And do take a look at all the other courses. Pretty much, the idea is what we speak here will stitch back into reinforcing whatever you learn from the other courses. Perfect. Okay, so with this, maybe we can close the call for today. Thank you for joining in, and we'll see you next time.
Thank you.
All right.
Bye bye.
Bye-bye.
Thank you. Bye.